Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about the following geometric constructions: inscribed polygons. Now, what are inscribed polygons? Well, according to the definition, an inscribed polygon is a polygon whose vertices are points of a circle, as you can see in the figure. So in today's lesson, we will be learning about the various inscribed polygons that we can construct inside a circle, such as the inscribed equilateral triangle, an inscribed square, an inscribed regular hexagon, an inscribed regular octagon, and an inscribed regular dodecagon. So we will be learning about these constructions, not necessarily in that order, because they are related to each other. So let's get started with our first construction. Okay, during our first construction, we will be learning how to inscribe a square inside a circle. And we're going to do this using the compass and a straight edge. The first thing we want to do here is to label a point for the circle, and let's call it a point O. And we want to construct a circle with its center at O. So we're going to take a compass and make the radius big enough so we can construct a nice circle as shown here in the diagram. At this point, how do we construct a square inside the circle? Well, the first thing we want to do is draw the diameter of this circle, because that's the only thing we can do at this point. So let's say we select a point here, and I'm going to call this point A. So now we can connect point A with point O and extend it backwards. And let's call that point C, because we are going to have two more points B and D over here. Okay, so it's going to be square ABCD. So this segment AC represents the diagonal of that square. So what we want to do now is draw the perpendicular of this segment. And all we need to do here is draw the perpendicular of segment AB by constructing two arcs, one on the left and one on the right, okay? And we could, technically speaking, also use the circle itself to do so. So then from these arcs of intersections, we want to choose a width on the compass that is more than half the width of these arcs of intersections, and draw two more arcs from each of these arcs of intersections. Okay, so now we have 2 points here, and we connect these points, basically this point with point O, and extend it like that. Okay, so now we're going to label this point as B, and this point we can label is as D. Okay, so now we got the diagonals of the square, and all we need to do is connect AB, BC, CD, and AD, okay? So the question is, why does this construction work? Because we do need a justification for this, right? So the justification for this construction is basically the property of the square, right? So let's write this in here. Properties of squares, okay? And let me actually also label this as a justification. Okay, so let me underline this. So the first property of the square, we know that the diagonals are perpendicular, and also the diagonals bisect each other. And another thing is that the diagonals are congruent. And when we have all these three properties here, you do end up with a square, okay? So that's really the justification of this construction. Okay, so now our second construction entails inscribing a regular octagon, okay? So how is this related to inscribing a square? Well, it's simply related by the fact that an octagon has double the amount of vertices compared to a square. So what we can do here is basically construct a square and then bisect each of the adjacent vertices. So let me actually demonstrate this, okay? So first, let's draw a circle. Again, I'm going to label this point O. So now we have 4 vertices. So if we would connect these points, we would have a square ACEG. But now what we want to do is bisect these angles, okay? So let's, for example, bisect angle AOC. And again, we know how to do that, to bisect an angle. So we draw an arc here like this, right? And then from these points of intersections with the arc and the segments, we pick a width so that we can draw 2 more arcs outside the circle. Like that. Okay, so now when we bisect this, we should also extend the line backwards, like that, okay? So this point now will become point B, and this point is point F, okay? And we can repeat the steps now for, let's say, angle COE. So again, we want to draw an arc here. So let me actually pick the same width here of this arc here, okay? Just to be consistent so that the drawing looks a little neater. And again, we draw 2 arcs outside the circle here from these arcs of intersections. Okay, so now we can draw the segment, which is the angle bisector, okay? And extend the segment backwards to intersect the circle on the other side. And let's call that point D, and that point, so we have point H over here, okay? So all we need to do now is connect all the consecutive points on the circle, or the consecutive vertices, so to speak. And once we connect this, we will obtain a regular octagon, okay? There you go, is our regular octagon here. And again, the justification is simply based on the construction of the square itself. So our third construction is how to inscribe a regular hexagon inside a circle O as shown here in the figure. So in order to do this, we first need to draw a radius, okay? So let's, for example, pick a point on the circle. Let's call it point A. And what we want to do here is connect point A and O and actually extend it backwards, okay? So our hexagon or regular hexagon will have points on the circle. So we actually do need another 2 points on the circle, right? So we need 1, 2, 3, 4, 5, and 6. And they all have to be equidistant. And the way to do that is by measuring the radius, okay? So we already have it set for the radius. And we are going to copy the radius over until we reach point A again, okay? So this should actually coincide here, which it does. Now at this point, we continue by drawing 2 more arcs, and the last one again should be coinciding here. Okay, so at this point, we just label these. So we label this as point B, point C, point D, point E, and point F. And that's it. All we need to do now is connect these consecutive points to make a regular hexagon inscribed inside this circle O. Okay, so there it is. That is the inscribed regular hexagon. Now let's talk about the justification. Okay, so why does this work? Why is it that if we copy the radius around the circle, we end up with equidistant points? Well, we can think of it as follows. So this is the radius r, okay? So what we did here, when we copied the distance from O to A, that is the same as the distance from A to B. So that's also r. So these two segments are congruent. So what can we say about this segment over here? Segment OB. Well, that is also the radius of the same circle. So it turns out that all these segments that are being drawn here, they're all congruent, okay? All these segments, they're all represented by the radius r, okay? And again, the reason is because radii of the same circle are congruent, okay? So when we copied over these distances, these are also represented by r, and these are also congruent, okay? So these are all called r. Now, what kind of triangle do we obtain here? If you look at, for example, triangle AOB, all the sides are congruent. So we end up with equilateral triangles, okay? Now, when we have an equilateral triangles, let me write this here, equilateral triangles. When we have equilateral triangles, what do we know about the degree measure here? Well, we know that this is 60 degrees, okay? So we know that this is also 60 degrees. This is 60, this is 60, this is 60, and this is 60. And as a matter of fact, 6 times 60 degrees is 360 degrees, okay? So we also know that this is 60 degrees. So they're basically all 60 degrees, okay? So if you do the math, each of these angles here, so let me shade it in. So this angle, for example, is 120 degrees, okay? This is 120. So let me shade that in. This is also 120. This is 120. 120 and 120 over here. And finally, we have another 120 degrees over here, okay? So when you end up with a polygon with congruent interior angles of 120 degrees, okay? So these are considered the interior angles. So when we have a scenario like this, you actually do end up with a regular hexagon, okay? So there's no other shape other than a regular hexagon that has this property that the interior angle is each 120 degrees. So that's basically the justification for the third construction. So our fourth construction entails inscribing an equilateral triangle. So how do we do this construction? Well, we have to think about how is this related to constructing a regular hexagon. Well, in that case, we just need to skip every other vertices. So let's see what we're talking about here. So for example, let's say we put point A here, okay? So we know that this is now the radius from A to O, okay? So let's pretend that we are constructing a regular hexagon, and as we learned in the previous video, all we need to do is copy the radius or the distance from A to O along the arcs here, okay? So let's do that. Okay, so we want to do this nice and neat. Okay, so now instead of connecting all the points of intersection, all we need to do is just skip every of these vertices, okay? So for example, we can call this point B, and this one, we can call it point C. And all we need to do now is connect these points, and there you go, we have an equilateral triangle. It's actually that simple, this construction here. Okay? So how do we justify this construction? How do we know that all these segments are congruent? How do we know that? Well, we also simply need to look at the angles here, okay? So for example, if we draw this one and we draw this line here, well, we know that these segments are congruent because these are the radii of the same circle. So the next thing is to think about the angles themselves, okay? So again, we know that if we connect this line over here, well, we learned it before that this is also congruent. Well, this is congruent, and this is actually 60 degrees, okay? So if we repeat the step, we know that this is also 60 degrees, okay? So it turns out that the interior angle here, so let me shade that in here, that interior angle is going to be 120 degrees, okay? Now, what kind of triangle is this? If you look at triangle AOB, we know that's an isosceles triangle because these sides are congruent. We know the vertex angle is 120 degrees, therefore this needs to be 30, and this needs to be 30, correct? So we just have to simply repeat the steps. We know that this is 120, and therefore this is 30 and 30. And this is also 120 degrees, and therefore this is 30 degrees, and this is also 30 degrees, okay? So if we look at this now we know that this angle over here, that's 60, this angle here is 60, because we just simply add up the two adjacent angles that are 30 degrees each, and we end up with an equilateral triangle with 60 degrees each, okay? So that's basically the justification. So our last construction involves inscribing a regular dodecagon in circle O. So how do we do that? Well, first we need to know what dodeca means in Greek, and it actually means 12. So we want to inscribe a 12-sided regular polygon in the circle. Again, this is related by the fact that a hexagon has 6 sides, so we can actually double the sides by basically bisecting the angles of a regular hexagon. So the first thing we need to do is construct a regular hexagon. Now, instead of me connecting the points here, what we want to do is bisect that angle here, okay? Maybe it's better visible if I do the following, if I draw this line over here, okay? So we want to bisect this angle. So what we can do, we can actually now use this arc to bisect the angle, and we just put the point here, or we put the compass at this point, and we draw 2 arcs outside like this. So we're going to draw an arc here and another one from A, such that they intersect outside, okay? So now all we need to do is connect this point of intersection of the arcs to O, and we should actually extend it backwards as well, okay? Because it's going to bisect that arc as well here. Okay, so now we got 2 points here, and let's call that point B. So this is our point C, and now we need to bisect this angle and this angle, okay? So we need to do this one more time, or I should say 2 more times. So we draw 2 arcs here, and we'll do the same thing for here, okay? There you go. Okay, so now all we need to do is draw these segments and extend it backwards. There you go. Okay, so we're basically done, and all we need to do is connect these points by a segment, okay? And there you go, is our regular dodecagon, okay? So with inscribed polygons, we simply have to think about the number of sides and what else can we draw. For example, if we have a square, if we can draw or construct a square inside a circle, then we can construct an octagon, a regular octagon, by bisecting its angle. And we can continue by constructing a regular polygon with 16 sides, and so on and so on. Similarly, also with a hexagon, since the number is 6, we can construct a polygon with 3 sides, which is the equilateral triangle, or with 12 sides, which is the dodecagon. Anyway, so that's basically it for today's lesson. I hope you enjoyed it, and have a wonderful day.